Hi everyone, today we will talk about learning the deformation of polydomain liquid crystal elastomers with constitutive artificial neural networks. Liquid crystal elastomer is characterized by interwoven networks of liquid crystalline mesogens and amorphous polymers. It can produce large deformation responses to external stimuli and is used in soft robotics and actuators. Due to its complex microstructures, modeling liquid crystal elastomers is very challenging. Traditional theoretical modeling of liquid crystal elastomers is mainly based on phenomenological approaches. However, constitutive artificial neural networks provide a new way of constitutive modeling. It is thermodynamically consistent, considering material symmetry and objectivity. Therefore, in this study, we will learn the finite deformation of liquid crystal elastomers with constitutive artificial neural networks.
The methodology of our work is largely based on the data from the paper titled Modeling the Deformation of Polydomain Liquid Crystal Elastomers as a State of Hyperelasticity. The paper contains many sets of data on LCE that are useful for testing our neural network model. The neural network code that we have chosen is invariant-based, that is based on the original code from the brain can. But we have changed the formula for long due to running into some instability while training some data. We then use a variety of data from the paper above to validate our model. Here's a comparison of our equation used for the invariant model against the original equation from the brain-can invariant model. The small change was found to be much more stable for handling a variety of data sets. We tried to incorporate third powers into the equation, but the result was trivial or worse for the additional computing resources needed. Lastly, here's a diagram of the data we use for testing the neural network model.
This is the result of our revised CAN. Each column represents to each test, and the top row is the results from the uniaxial tension test, and the bottom row is the pure shear test. And you can see CAN performs pretty well to fit all data. And here I want to mention that because the LVEC is a very complex, large finite deformation problem, our largest stretch is even larger than 6. So it proves that CAN has the ability to solve the large finite deformation problem. And next, I want to briefly talk about the reason we changed our activation function. The left-hand side is the original function. You can see that it's very sensitive to the large deformation, but the right-hand side, our revised version, can provide more lower value in the large deformation region. And in the future, we were going to test the stretch-based model and compare the results with the invariant-based model. Thank you.